In this lecture, we're going to be looking at division of polynomials. We're going to review both long division of polynomials and synthetic division. And our overarching goal is to learn how to use division of polynomials to help us factor. When we're dealing with a higher degree polynomial and our standard tricks like grouping don't work, we're often going to fall back on guess and check by using division of polynomials. In order to be able to do that effectively, we have to remember how to divide polynomials. So let's do some examples. This first example says divide x squared minus 5x plus 6 by the binomial x minus 2. Now I choose to do this example first because we can find the correct answer another way. The numerator factors, and this is one that we know how to factor. This factors to x minus 3, x minus 2. And we can cancel the factors of x minus 2, so the answer should be x minus 3. We know what the answer is going to be ahead of time, x minus 3. But I want to get that answer not through this process, but through long division. I'm going to set this up like a long division problem, the same way you would with numbers. I'm going to take the divisor, which is the denominator, and put it on the outside of the division bar. I'm going to put the dividend, which is the numerator, underneath the division bar. And we're essentially going to use the same process you use when you divide numbers. Just a quick reminder of how we do that. If I want to divide, say, 32 into 2048, I start by trying to figure out how many times 32 goes into 204. I don't bother trying to divide it into 2 or into 20 because 32 is bigger than both of those. So I start with the 204. And here we have to do a little bit of guesswork. But since 3 goes into 26 times with a remainder, I'm going to guess that this is 6. Then I multiply down. 6 times 2 is 12. I carry that 1. 6 times 3 is 18 plus the 1 that I carried is 19. And then I subtract. 204 minus 192 is 12. And then I bring down the 8, right? And then I play that same game again. 32 into 128, well, I'm going to guess 4 since 3 goes into 12 4 times. 4 times 2 is 8. 4 times 3 is 12. We call the number on top the quotient, and this is the remainder. And because the remainder was 0, we say that 32 divides into 2048 evenly, or another way to say that is that 32 is a factor of 2048. In fact, what we've shown is that 32 times 64 equals 2048. 32 is a factor of 2048. I'm going to follow that exact same process over here, except in my opinion, this is even easier because there's no guessing. Here I had to guess that 32 goes into 204 6 times. Here there's no guessing. I ask myself, how many times does x go into x squared, or what is x squared divided by x? I can just do this off to the side. X squared divided by x is x. And so the first term of my quotient is x. What did we do with the 6? Well, we multiplied down. I do the same thing here. I take x times negative 2, that's negative 2x. Then I take x times x, that's x squared. And you know something's going right if these match. The first term should always cancel away in your next step. We're going to subtract. When you subtract a polynomial, you switch all of the signs. Now we collect our terms together. X squared minus x squared is 0, those canceled. Negative 5x plus 2x is negative 3x. After we subtracted in the numerical example, we brought down the 8. I'm going to bring down the next term here as well. I bring down the 6. And now we start the algorithm all over again. I ask myself what times x would give me negative 3x, or without guessing, I can just divide. Negative 3x divided by x. That's negative 3. The next term of my quotient is negative 3. I multiply down. Negative 3 times negative 2 is positive 6. Negative 3 times x is negative 3x. I'm subtracting, so I switch all of the signs. And I get a remainder of 0. Because the remainder is 0, we say that x minus 2 divides evenly into the polynomial, and our quotient is x minus 3, which is exactly what we got by cheating when we factored first. Let's do a couple more just to make sure we cover all the bases here. This second example says x cubed minus 8x squared plus 5x minus 7 divided by x squared minus 3. I'm going to start by writing the divisor on the outside and the dividend underneath the division bar. And now I divide the leading term of the divisor into the leading term of the dividend. So that's x cubed divided by x squared, which is just x. I multiply down. 3 times negative x is negative 3x, and make sure you line that up under the x term because those are the like terms. X times x squared is x cubed. I switch the signs, which is going to make that first term cancel away. We're switching the signs because we're subtracting, just like you would do with integers. X cubed minus x cubed cancels. I bring the negative 8x squared down. 5x plus 3x is 8x. And I bring down the minus 7. Now I start the algorithm all over again. How many times does x squared divide into negative 8x squared? You probably don't have to show this work off to the side, but let me just stay consistent and keep doing it. Negative 8x squared divided by x squared is negative 8. So the next term of my quotient is minus 8. Then I multiply down. Negative 8 times negative 3 is positive 24. That goes underneath the constant term. Negative 8 times x squared is negative 8x squared. I'm subtracting, so I switch the signs. The x squared terms cancel away. The 8x comes down, and negative 7 plus negative 24 is negative 31. And at this point, what's left over has a smaller degree than our divisor. We call this a remainder. The remainder this time is not 0. So x squared minus 3 is not a factor of x cubed minus 8x squared plus 5x minus 7. The way that we could write our answer is to say that this is x minus 8 plus our remainder over our divisor. You've done this before with numbers too. Let me do a simple example. When we divide 3 into 13, it goes in 4 times with a remainder of 1, and we're taught to write that as 4 1/3, which means 4 plus 1/3. We just don't write the plus sign because it's implied in the notation. We're doing the exact same thing here. We put the remainder over the divisor. We put the remainder over the divisor. Same idea. Another way we could write our answers just to express what the quotient and the remainder are. We could say that the quotient is x minus 8 and that the remainder is 8x minus 31. What's ultimately important to us in the long run is that the remainder isn't 0. Because the remainder isn't 0, that means that x squared minus 3 is not a factor of the original polynomial. Because x squared minus 3 isn't a factor, we would lose interest at this point. As soon as we saw that the remainder isn't 0, we would move on and see if there's some other factor. That's how we're going to use this to try to factor. One more example of this, just to show you one more thing you have to watch out for. Here we've got 4x cubed minus 2x plus 15 divided by 2x plus 3. So divisor on the outside, dividend underneath, and I notice this time that there's a term missing. There's no squared term. I need to put in a placeholding 0 for that. This is just to make everything line up. Without that in there, things would get jammed up quickly. Now we start our algorithm. I divide 4x cubed by 2x. That's 2x squared, so the first term of our quotient is 2x squared. I multiply down. 2x squared times 3 is 6x squared, and now you see why I put in the x squared term. It gives me a place to line that up. 2x squared times 2x is 4x cubed. Always a good sign if these match. If these don't match, you've made a mistake. Switch the signs because we're subtracting. 4x cubed minus 4x cubed is 0, good. 0x squared minus 6x squared is negative 6x squared. And then I bring down the next term. I play the same game. I take negative 6x squared and I divide it by 2x. That's negative 3x. That's the next term of my quotient. I multiply down. Negative 3x times 3 is negative 9x. Negative 3x times 2x is negative 6x squared. It better be, or else we messed up. These are supposed to cancel. I'm subtracting, so I switch the signs. The squared terms cancel away. Negative 2x plus 9x is 7x plus 15. And now one last step. Don't let it bother you. 7x divided by 2x. That's 7 halves, or 3.5. You could use the decimal. The last term of our quotient is 7 halves. 7 halves times 3 is 21 halves. 7 halves times 2x is 7x. We're subtracting, so I switch the signs. The 7x's cancel. 15 is equal to 30 over 2. 30 over 2 minus 21 over 2 is 9 over 2. Is 2x plus 3 a factor of this? No, it's not, because our remainder isn't 0. The quotient is 2x squared minus 3x plus 7 halves, and the remainder is 9/2. Now, when your divisor is a linear expression with leading coefficient 1, like in our first example, x squared minus 5x plus 6 divided by x minus 2, you can use another technique that's called synthetic division. Synthetic division allows us to avoid recopying all of these unnecessary terms, but it relies on the fact that you're dividing by a linear expression with a leading coefficient of 1. Here's how it works. List the coefficients of your dividend. So the coefficients are 1, -5, and 6. I don't need any placeholders here. This stands for 1x squared, this is -5x, and this is the constant term. And then off to the side in the little nook, we're going to write the value of c. Notice that we're dividing by x minus c, so c here is 2. That effectively switches the sign. Remember, every time when we subtract, we have to switch the sign? That step essentially takes care of that. I'm going to draw a line, and now you drop the very first coefficient down. And if you want to know why you get to do that, it's because you're dividing by x. So x squared divided by x will be 1x, and so the coefficient of the first term of the quotient will be 1. You then multiply, you take 1 times 2 and you get 2. And then you add these together. We've already switched the sign, so we don't need to subtract. That gives us -3. Then we multiply, 2 times -3 is -6, and we add these together to get 0. These are the terms of the quotient, and the last part is the remainder. And because we're dividing by x, each term of the quotient is 1 degree smaller than the terms we were dividing into. So since this was an x squared, this is an x term. And since this was an x term, this is the constant. And then since this was a constant, this is the remainder. So our quotient is x minus 3, and our remainder is 0, which is exactly what we got when we did it by long division. The procedure that I used here only works if you're dividing by x to the first power. The fact that you can just drop this coefficient down and just add these together is dependent on the fact that you're dividing by a 1x. If you're dividing by a quadratic expression, or if you're dividing by a linear expression with a leading coefficient of something other than 1, then our process doesn't work. Let's try another example. 5x cubed plus 4x squared minus 6x plus 1 divided by x plus 3. So I list the coefficients of the dividend, the thing on top, 5, 4, -6, and 1. And off to the side in a little nook, I put the value of c. Here we're adding 3, so the value of c is -3. Again, I like to explain this like we're switching the sign from the start so that we don't have to worry about switching the sign down here. I get to bring the 5 straight down. And again, a lot of people ask, why do you get to do that? Well, think about what the first step would be in long division. We would do 5x cubed divided by x, and that would be 5x squared. That first coefficient isn't going to change. Then you multiply, you take -3 times 5. That's like taking the 5 in the quotient times the 3 right here, and then switching the sign. So we get -15. Then we add, we don't subtract because we've already switched the sign. That's -11. Then we multiply, -3 times -11 is +33. Then we add, it gives us 27. Then we multiply, -3 times 27 is -81. And then we add, and we get -80. So x plus 3 definitely isn't a factor of the numerator because our remainder wasn't 0. We got a quotient of 5x. What power would this be? Well, this was x cubed, so this guy is x squared. Minus 11x plus 27, and our remainder was -80. We'll see in a moment that that remainder means something else, but let me do one more example of this. I want to do one with a missing term. This one, in fact, has 2 missing terms. We're doing x to the 4th minus 6x squared plus 8 divided by x plus 2. So I list my coefficients. This is 1x to the 4th, but I have to put in a placeholding 0 to show that there's no x cubed term. Then a minus 6x squared, and then a placeholding 0 to show that there's no x term, and then the constant term. Off in the nook, I'm going to write a -2. That's the value of c. I get to bring the first term down. Then I multiply. -2 times 1 is -2. I add. I multiply. I add. I multiply. I add. I multiply and I add, and hey, this came out to a remainder of 0. X plus 2 really is a factor of that polynomial. We just showed that the quotient is, well, let's see, this was an x to the 4th, so this must be an x cubed. So it's x cubed minus 2x squared minus 2x plus 4, and our remainder was 0. And when the remainder is 0, that means that the denominator is a factor of the numerator. We have in fact just showed that we could factor x to the 4th minus 6x squared plus 8 as x plus 2, that was the divisor, multiplied by our quotient, x cubed minus 2x squared minus 2x plus 4. If we wanted to get x to the 4th minus 6x squared plus 8 factored completely, we can now work on trying to factor x cubed minus 2x squared minus 2x plus 4, which we could either do by guessing other factors and trying division, or this one will actually factor by grouping. If you get bored later, you can try to finish this off by factoring this by grouping. I can only hope you don't get that bored. Okay, I mentioned that there was an interesting fact about the remainder in that previous example, and this holds true in all examples. If you divide a polynomial f of x by x minus c, then the remainder is always what you get when you plug c into the polynomial. Let me show you what I get when I plug negative 3 into that polynomial. 5 times negative 3 cubed is negative 135. 4 times negative 3 squared is 4 times 9, that's 36. Negative 6 times negative 3 is positive 18, plus 1. Negative 135 plus 36 is negative 99. 18 plus 1 is 19. And negative 99 plus 19 is negative 80. That's not luck. The remainder is always equal to what you get when you plug the value of c into the numerator, into the dividend. A long time ago, this was a useful fact for evaluating polynomials. In the age of calculators, that's kind of fallen by the wayside. But there's another important thing that we can deduce from this. In particular, this is special with the output of 0. We call this the factor theorem. A polynomial has a factor of x minus c if and only if f of c equals 0. So let me show you how I use this. I made up this example x to the 4th minus 6x squared plus 8 divided by x plus 2. And how did I know in advance that x plus 2 was going to be a factor? Well, I just plugged negative 2 into the function. If I plug negative 2 into that function, I get negative 2 to the 4th minus 6 times negative 2 squared plus 8. And when I evaluate that, I get 16 minus 24 plus 8, which is 0. So I knew x plus 2 was going to be a factor. I didn't actually have to do the division. I didn't know what the other factor was going to be, but I knew that it was a factor automatically because when I plug negative 2 into that expression, I get 0. So when we're trying to factor in the future and we really have no leads on what the possible factors are, we can just start plugging numbers into the function. And if we find a number that gives us 0 as an output, well, then we know x minus that number has to be a factor, and that can get the ball rolling when we're trying to factor. To end the video, we're going to do some examples using this factor theorem, and we're going to use it in both directions, an if and only if statement has two directions. One of the directions of this theorem says this: if f of c equals 0, then x minus c is a factor of f of x. Now, how would you use that? Well, we'd use that when we're trying to construct a function. Like here's an example, very generic, no application here. Find a polynomial f of x of degree 3 with leading coefficient 1 and having zeros of 7, negative 2, and 4. Well, how would we do that? Well, one direction of the factor theorem says if f of c equals 0, then x minus c is a factor of the function. Since 7 is a 0, that means that x minus 7 must be a factor of f of x. It has to be. You can see how it works. Plugging 7 into that is how we're going to get 0. Since positive 2 is a 0, that means that x plus 2 must be a factor. It's like x minus negative 2. And since 4 is a 0, that means that x minus 4 must be a factor. So we've met this condition that we've got the right zeros. Let's see, do we have leading coefficient 1? Well, sure, we didn't multiply by anything out front. And do we have degree 3? If we were to multiply this out, this would be third degree. This is a perfectly acceptable way to answer this problem, but I'm going to multiply it out just so you can see what it would be if we multiplied it out. I want to show you that it meets all of these conditions. So you can see that my final answer has degree 3 because the highest power is 3. It has leading coefficient 1. The leading coefficient is 1. And you can't immediately tell that 7, negative 2, and 4 are zeros of this, but they were zeros of the original factored form, so unless I made a silly mistake in my arithmetic, this should work. I checked it and then edited out the check so you wouldn't have to watch me do it. Those are all zeros of this polynomial. So that's one way to use the factor theorem. If c is a zero, then x minus c is a factor. The other way to use that is in the opposite direction. This also says if x minus c is a factor of f of x, then f of c must be equal to 0. This is the one that we'll use when we're trying to guess factors. You're trying to find factors of a complicated polynomial, and you're essentially just guessing. And you don't want to have to do the division. Like, look at this example. Here I've asked, is x minus 1 a factor of f of x equals x to the 9th minus 2x to the 5th minus 6x cubed plus 7? You don't want to test that by using long division. You don't even want to do it by synthetic division. You'll see why in a moment. We've got a shortcut though. We can just plug 1 into the function. Remember that we plug in 1 because we think of this as x minus c. So I plug 1 in for x and I evaluate it. This is 1 minus 2 minus 6 plus 7, which going across here, 1 minus 2 is negative 1, negative 1 minus 6 is negative 7, negative 7 plus 7 is 0. So yes, x minus 1 is a factor of that function. I'm not going to write it out, I'm just going to write f of x. And I can prove it to you. I did the synthetic division for you right here. I wrote 1 off in the little nook. I had to put tons of placeholding zeros in here because we're missing an 8th power, 7th power, and a 6th power. We're also missing a 4th power, and then we're missing a squared term and a linear term. So I had to put in all these placeholding zeros. I did the synthetic division, which wasn't hard. It was just arduous because there are so many terms. But notice that I got a remainder of 0, and so I can factor x to the 9th minus 2x to the 5th minus 6x cubed plus 7 by multiplying x minus 1 by this ridiculous polynomial. Notice how much easier it was to check if it was a factor by just plugging in 1. It would have been a real punch to the gut if we had done all of this work the long way and then not got a remainder of 0. Then it wouldn't have been a factor and we couldn't have used that anyway. It's so much more convenient to just plug a number into the function and see if you get 0 before you try doing the division. So the factor theorem allows us to check for factors without having to actually do the division. It's pretty nice. Let's do that a couple more times. I would have quite a few people who would say that x minus 4 is a factor of this because they would try factoring this by grouping. They would do x squared times x plus 1, and here they would do negative 2 times x minus 4, and they see that x minus 4 and they think that it's a factor. Well, let's see if x minus 4 is a factor, and I'm going to do that not by doing the division, but just by plugging 4 into this function. 4 cubed plus 4 squared minus 2 times 4 plus 8. There's no way that's going to be 0. That's 64 plus 16 minus 8 plus 8. That's 80. We didn't get 0, so no. X minus 4 is not a factor of that polynomial. I wouldn't bother even trying to factor with x minus 4. I would not use synthetic division or long division here in order to try to get this broken down because x minus 4 isn't a factor. I'd like you to do this one for me. Is x plus 2 a factor of x cubed plus 8? Check that with the factor theorem. To check this with the factor theorem, you plug negative 2 into the function. X plus 2 has a c value of negative 2. So that's negative 2 cubed plus 8. And yeah, that's 0. X plus 2 really is a factor of x cubed plus 8. Some of you might have known that because x cubed plus 8 is a sum of cubes and there's a formula for this. But that's kind of my point. I want to show you how to use this to factor x cubed plus 8. A lot of people know that x cubed plus 8 factors to x plus 2 times something, but some people have trouble remembering what that something is. You don't have to remember anymore. Now we can divide. You can either do this by long division. You can divide x plus 2 into x cubed plus 0x squared plus 0x plus 8, or you can do it by synthetic division. We put negative 2 into the nook and use the coefficients 1, 0, 0, and 8. I don't care which way you do it, but do the division and come up with the other factor. I'm a much bigger fan of synthetic division when it's an option, so that's how you're going to see me do it here. I drop the 1, 1 times negative 2 is negative 2, 0 plus negative 2 is negative 2, negative 2 times negative 2 is 4. Add together, 0 plus 4 is 4, negative 2 times 4 is negative 8, and 8 plus negative 8 is 0. We should not be shocked by this remainder of 0. we just showed that it was a factor. Since this was a cubic term, this is a squared term. So our other factor is 1x squared minus 2x plus 4. And if you remember your sum of cubes formula, that will not surprise you. If you're a little rusty on your sum of cubes formula, well, good news. You don't have to remember it anymore because now we can use this to factor. Yes, it's probably faster to have it memorized, but formulas like this, the sum of cubes formula that you don't use very often, they might slip your mind. That's okay. Now we can just factor it this way. So this factor theorem here is something we're going to use quite a bit in upcoming sections. When we're looking for factors of a polynomial, we can just plug numbers into the polynomial and see whether or not we get 0. And if we get 0, then we're off and running with our factoring. And if we don't get 0, then we know not to waste our time with that factor. It's really nice. In order to get it factored, once you know that you've got a factor, in order to get it factored, that's where the division comes in. And you can do that with long division or synthetic division. I'm pushing the synthetic division because it's so concise. I don't have a problem with you using long division, though. You're welcome to use that instead. So in this lecture, we reviewed synthetic division and long division. They're supposed to be prerequisite to the course, but if you're rusty on those, you need to practice that. And then get used to using this factor theorem. Do some problems where you're just checking for factors of a polynomial. We'll get more practice factoring in future sections. If you have any questions for me about either of the division techniques or about how the factor theorem works, just reach out to me. You can catch me in an office hour or you can shoot me an email.